Good day, everyone. This is Chris again. I know that I had said that I was going to kind of quit at 2 videos on the quantum numbers, but I just wanted to talk about a couple more points, simply because I think some of what I said may be a little confusing to people. When I talked about the quantum numbers, I said, look, there are 4 numbers that come out of quantum mechanics. And really what we're talking about with the quantum mechanics, as far as chemistry goes, we're talking about the Schrodinger equation. The Schrodinger equation. And really, when we talk about chemistry, we're talking about what we call the time-independent Schrodinger equation. And in its simplest, or its most reduced form, it looks something like this. And I'm not really going to go into a whole lot of details, simply because the math is pretty complicated, a lot of calculus involved, and derivatives and so on and so forth, but we'll just give you kind of a general idea. So this is the Schrodinger equation, and we have h hat equals psi. Psi is what's known as the wave function. Because again, we have to treat electrons, we have to treat them like waves sometimes and particles other times. So we do use a wave function and wave mathematics to describe some of the electron's behavior. Equals E, energy, special type of energy, and that actually becomes a constant. Again, it's just not really important to talk about in depth at this point. And psi. Now, this h hat, this is called h hat, is a little interesting. And the best way of describing it, at least classically, when we talk about Newtonian dynamics in classical mechanics, is this h hat is analogous or an analog of the Hamiltonian. So this h hat is actually what we would call an operator. So the h hat operates on or acts upon the wave function. What is a Hamiltonian operator? What is the h hat of the Hamiltonian? Well, it's basically just talking about energy, and it's talking about the 2 types of energy that we can run into with moving matter, like electrons. We can have kinetic energy, and we can have potential energy. So I take that, I add it up, and obviously it's a bit more complicated than that. I put all that together, I throw it into the Hamiltonian, or I throw it all together, and it becomes a Hamiltonian operator. And that, what I mean by operator is it actually operates on psi, or on the wave function. Okay, well that's pretty interesting and pretty complicated and so on and so forth. But why did I just talk about that? Well, I just wanted to kind of give you a little better visualization of this mysterious Schrodinger equation that I've been talking about. That these numbers, these quantum numbers, just kind of pop or fall out of the Schrodinger equation. And what we generally end up doing is we'll solve for the wave function psi, and obviously we're talking about 3-dimensional space, an electron where it is in 3 dimensions. So you'll solve it for either the x, the y, or z. And as you get a little more advanced, the x, y, z axis are actually x being horizontal, y being vertical, z kind of being the spatial dimension. When we go a little more in depth, these are what we call these Cartesian coordinates. We actually start dealing with what are known as spherical coordinates, which are a little more complicated. But when we get to the wave function, we actually solve it, and the Hamiltonian and all that, what it tells us is, well, it doesn't actually tell us much anything at all. It tells us nothing. Schrodinger was actually confused himself when he first derived this and came up with this, because he had no idea what in the hell psi, the wave function, told us. And it wasn't until a physicist by the name of Max Born figured it out and said, well, what I can do is, I take the square of the absolute value of the wave function, so psi squared, that is what gives me a probability density. And remember when I talked the last lecture, or the last couple of lectures, that these orbitals, the s, p, d, and f orbitals, are nothing but electron densities, or a probabilistic way of looking at finding out where an electron is. So that's kind of some of the background behind these quantum numbers. Now let's kind of get to the point. I think when I talked about the quantum numbers, I said, look, you have four of them. You have your n, your l, your m sub l, and your m sub s. And we knew that the n number was your principal quantum number, corresponds to the period on the periodic table. And then I said the L is the orbital, and you have your S, P, D, and F orbitals that we deal with. Theoretically, there's a lot more, but this is what we deal with on a practical basis. And then I talked about M sub L as being the magnetic number, and then M sub S being the spin number, the intrinsic angular momentum. I think where I may have confused people is I said, well, look, the M sub L determines the shape of the orbital. So the orbital M sub L determines the shape, I think is what I had said. And that's not totally accurate. It can determine the shape of some orbitals. Certainly when we talk about like the D or the F orbitals, they're a little bit more complicated. They can take on really complicated shapes. So yes, the M sub L, the magnetic number, can determine or can tell us about the shape of the orbital, but not always. The L number tells us what type of orbital we're dealing with, and certainly that can take on, those different orbitals can take on very strange shapes. But the M sub L, what it really deals with is the magnetic orientation of an orbital, and they actually found this out, this M sub L, when they were looking at gases, emission absorption spectra from gases, and they'd actually expose certain gases to magnetic fields, and they would get these interesting results, these different lines. And they finally figured out, oh, wait a minute, you know, the magnetic fields are actually changing the orientation of these orbitals. So what I mean by that is, I'll just go ahead and give you an example to kind of better describe that. And I'm going to go ahead and I'm going to talk about the p orbitals, just because they're a little easier to look at. And what a p orbital is it's a little different from an s orbital. You know, the s orbital takes on kind of a circular shape. If I have the nucleus here, and then it takes on an area of electron density or electron probability around the nucleus, and we call that an s orbital. Well, the p orbital has something called a node in it, and when you run it through the Schrodinger equation, all that, my s orbital, you know, might look, oh, I don't know, something kind of like that on a graph. Well, if I were to graph the p orbital, it would look something kind of like that. And you see, I have a little area here of no probability of finding that that electron, and that's what we call a node. And the way that looks is, if I have my nucleus here, around the nucleus I'm going to have an orbital, and then another area, and then I have a node right about at the nucleus where I'm not going to find no electron, and then I have my areas of high probability of finding an electron. So high probability in these areas. Now, the shape of the p orbital is you know, somewhat circular, but the way it's oriented is actually dependent highly on that m sub l. So if we go back to our quantum numbers, and let's say I have n, and we'll make n2, L can either be 1 or 0, m sub L be negative 1, 0, 1, 0, m sub S plus or minus 1/2 spin. So what I'm talking about, these p orbitals, I'm actually talking about L equals 1. Well, if you look here, your m sub L, your magnetic number, I have a negative 1, 0, and a 1. Well, what that tells me is that I have three different orientations of an L orbital. And the three orientations are px, py, and pz. So 1 equals p, we know that, and then I have three different orientations. That's what the m sub L is really telling me, is that there are three magnetic orientations of that p orbital, x, y, and z. Well, what does that mean? Well, let's go ahead and just work it through here. And we'll use the old familiar Cartesian coordinates. So I have my x-axis here, I have my y-axis here. Okay. So if I have a px orbital, what I'm going to have is, and we'll just say that this is the nucleus, to kind of the nucleus of the atom, kind of keep it simple. I'm going to have my orbital aligned on the x-axis here, on the horizontal axis. Okay, so that's pretty easy. Well, what do you think of py? So we'll change that to py. Well, I'm going to have my p orbital oriented along the y-axis, like that. So x, y, and perhaps one of the least intuitive is the pz orbital. Well, because we're talking about 3 dimensions, right? We only have 2 dimensions. I have horizontal and vertical, x, y. Well, what we can do is we can actually add a z dimension here. Okay. And that is kind of a spatial dimension. So I have horizontal, vertical, and then a spatial dimension, kind of like coming at you in 3D. Well, I can also have a d orbital align itself along that spatial dimension of z. And of course my node of 0 probability being at the nucleus. So I hope that kind of explains the m sub L a little better. Again, I think I was a little confusing when I said that it's a shape. Yes, it can be the shape, but really ultimately what the m sub L tells us is the magnetic orientation of the orbital. Alright, thanks again, guys.